I am delighted to introduce Sven Apel for his talk. I've known Sven for 10 years. I first met him when he visited Austin. My research group, it was in late 2006, early 2007. He was here for 3 months. He was special then. I knew he was going places. His thesis received the best software engineering. He received the best software engineering award. Best thesis in software engineering. I'll get it out. It's early. In 2007 for Germany. Let's see. He created Feature House. I had built ahead, and Feature House was just elegant. I mean, that's really the first time I saw his work after his PhD. It was a great piece of engineering. Elegant work, I wish I would have thought of it. Elegance is what we need more of in software engineering. Let's see, in 2011, he had best paper at SPLC. Last year, he got a best paper award for in Modularity in Colorado Springs. Last year was a good year for you, come to think of it. You had 4 ICSI papers, 4. That's gotta be a record. And one of them was the best, it was ACM SIGSOFT Distinguished Paper Award or something like. It was very impressive. Okay. Let's see. Have I forgotten anything? I feel like Donald Trump. Is this guy good? No, this guy's fantastic. This guy's absolutely fantastic. If there's any hecklers, they're Bernie Sanders supporters, so throw them out. Okay. So you be good. Sven gives great talks. We don't want to put any pressure on you, Sven. No pressure at all. No, none whatsoever.
Thanks for the very nice introduction. Thanks for the invitation. It's a pleasure for me to talk here about my research work. And it's actually a story about my personal research career, my research path, and the misunderstandings I had and the enlightenments I had. But it's also a story of a whole community or sub-community. So not all of AO and modularity, but a sub-community that did. So yeah, modular reasoning. So you don't need to understand the system as a whole. So it's good for program comprehension, but it's also very good for analysis tools, right? So the analysis tool do not need to reason about all the details of the system. And one aspect that is not always important, but very often is variability, right? So once you decompose the system into modules, you can possibly combine these modules in different ways to create system variants. And that's very important in my personal research work, right? So then in the end, you have a configurable system. And in the 90s, there was the observation, so modularity is very nice, right? And but for some concerns, that's what I call it, for some pieces of functionality, it's inherently hard to implement it in terms of the module, right? So somehow you need to touch existing modules, multiple existing modules, which is then called code scattering, and apparently also then it is tangled with the implementation of that very module, and that's illustrated with that red thread here. And that was very important since from the beginning for the AO community, right? And the idea was, well, we also need to separate these cross-cutting concerns, right? So that's very important. It was a kind of dogma in aspect-oriented programming, and what people did, right? Let's pull out that code that is otherwise scattered or tangled and pull it in such a wool ball, and then you need can weave it back on demand, right? And very often, not always, very often it was the case that the mechanisms of implementing this wool ball and the weaving somehow differed from the mechanisms of implementing these modules and these plugging mechanisms. There have been attempts to unify that with class specs and many other systems, but somehow you need advanced mechanisms, right, to implement this weaving mechanism. And the point, or that was kind of first misunderstanding I had, is really, I really doubted that this separation of concerns, right, so the dogmatic approach of pulling out code and whatever it costs, that this is always desired, right? Or on the other way around, so if you have scattering and tangling, is that really always harmless? Is that really always undesired? And I had that feeling when I really worked with aspect-oriented systems. So here's just a little example. So here, at this time, it was quite an axiom in the AO community that is harmful or undesired and that is desired. And here's just an example when looking at Berkeley DB, right? Database system with a kind of canonical cross-cutting concern tracing, right? Very simple. And here we have the tracing within the delete operation. So that is kind of undesired because the implementation of the tracing concern is tangled with the implementation of the delete operation and the base database. And here, those things can be seen in research papers at this time, right? Here's a separated concern, right, with aspect J in that case. You can use also another language. And those examples you can see in papers of that time. And I doubted that this is, well, good in every case, right? So, of course, separation of concerns is very important, but in some sense, I had the feeling that cannot always be true, that that is a very good solution, because it's complicated, right? There's a lot of boilerplate codes, and the observation was that modularity comes at a cost. And we realized that a lot when doing experiments with modularizing database systems. For example, Berkeley DB. So we took Oracle's Berkeley DB and modularized it into a product line. So we started with a feature model. Here's just a small excerpt. And we wanted to have a very fine-grained system decomposition so that we can tailor the database system to embedded systems, right? And here we have the feature model, and we wanted modules for the get operation, the put operation, and so on. And we quickly realized that based on the example before, well, that's very hard. The code is looking very ugly, lots of boilerplate code and so on. So we ended up with removing modules, right? We said, well, these operations can't be concerns. These operations can't be modularized. It's just too expensive, right? So we ended up with a new feature model. So we removed modules and we removed variability. So in the end, we disabled 3/4 of all variants because it was so expensive. What we also did was using the preprocessor, which is inherently anti-modular, right? So we wanted to implement logging, which is very important for databases, right? And the point is logging is a kind of canonical, another canonical cross-cutting concern. But the logging behavior was so context-specific that mimicking the context in the aspects are so complicated that we said, well, the context is in the code, right? Just leave it there, use a preprocessor directive, it's just too expensive. We would have loved, you know, to put it in an aspect using a feature module or an aspect, but it was just too expensive, right? And we also did other nasty things. So that was a first insight, right? So separation of concerns is very important, but it comes at a cost, and I will get back to that point. Another observation at this time arose from the discussion with people from other communities, right? So like from the object-oriented programming community or programming languages community, they said, well, code separation is very important, right? You need to separate concerns, but what guarantees do we have with regard to the result we want, right? The actual running program. So behavior is, of course, very important. And the point is separation of concern somehow helpful for that? Can separation of concerns give you any guarantees with regard to the resulting behavior of the composed system? And I know, of course, that in the aspect-oriented development community, people were concerned with semantics and program behavior. But especially in the early 2000s, people were somehow focused on code organization, right? Separation of concern at the code level. So, but I realized it's very important, and I noticed, well, that's a whole community, actually, which is kind of separate from the modularity or aspect-oriented software development community. So that's a feature interaction community, right? And here are two definitions of feature and feature interaction, and I hope we do not discuss these definitions, so let's just take them. So that's the definition of a feature. It's a prominent or distinctive user visible aspect, quality, or characteristic. So that's the definition from the product line community. That's pretty vague, but it's less vague than the definition of a concern. So the important thing here is that these concerns are user visible, and in this sense they are a means to communicate across or among stakeholders. And very often in that domain, features are domain abstractions. They're not arbitrary things, right? They're in an application domain and abstraction that is well known. So that somehow limits the set of possible features you can reason about. And I noticed that in research papers, when they talked about concerns, they just, came up with arbitrary concerns to make their point, right? Because a concern can be everything, right? And that's a little bit more narrow and more guided, right? Because typically the features come from the domain analysis, which is part of the domain engineering process in product lines. So anyway, feature interaction is some way in which a feature or features modify or influence another feature in defining the overall system behavior. So that's a standard definition from the feature interaction community. And the important point is here behavior, right? So I want to reason about individual behaviors or features and the overall behavior. So there's a certain focus here. And I found it very interesting. But especially I found interesting the relation between cross-cutting and feature interactions. And at this point in the early 2000s, I felt that there was a lot of confusion, but actually the relation is. So some people equated it. Some people said that's completely disparate concepts. The point is that indeed, at the conceptual level, feature interactions and cross-cutting are orthogonal concepts, right? You can have cross-cutting, but no feature interaction, and you can have a feature interaction without cross-cutting. But there should be a correlation, right? And that's very interesting, and I always felt that this connection, that correlation is somehow overlooked. And there's some research work, for example, by Gail Murphy, people who looked at the correlation, but there should be much more work, and later in that talk I will, tell a little bit more what we can do in that direction. But it's not the same. Okay, so let's talk a little bit about feature interactions, because I had very many misunderstandings, and I also found that many people had misunderstandings. The first important observation is feature interactions are not always undesired. So in fact, there are people like Pamela and Michael Jackson that most feature interactions are desired, right? So they think in terms of feature interactions when designing systems. That's what Michael Jackson is doing, for example. So here we have a desired interaction in a database system, right? So we have a transaction management feature and a statistics feature. So you can, following the modularity principle, can put them in modules. But these features need to communicate. They need to know about each other. For example, in transaction management, you want to do self-tuning, and you need statistics for that. That's state of the art. And in the statistics feature, of course, you want to know about transactions, to log transactions per second, not only for the transaction features, but for the administrator, right? So somehow these features need to be coordinated. There needs to be coordination code, which implements the interaction. So that means we have a problem when we want to modularize features, which are essentially concerns, right? Where do we put that coordination code, which can be quite substantial? And there are different ways to cause it. Prehofer called it lifters, Don called it derivatives, and so on, right? But what to do with that? So you may say, well, we don't care, right? But it's really a matter of scale. So you may have very many pieces of coordination code when the number of features grows, even exponential, of course, in the worst case. And, well, we asked, is that really a problem? So we looked at Berkeley DB, which is really a real-world system, right? And here are a couple of features of Berkeley DB, and we looked for coordination code between the features. That's really not assignable to individual features. And that's maybe not so interesting. Interesting is more the diagram, where we have the number of features and the number of pieces of coordination code. And we observed a smooth polynomial trend, right? The point is that it's not exponential in the worst case, but in the end, if you really want to modularize all these pieces of coordination code or somehow to handle them, you have even more pieces of coordination code than features, which somehow destroys the idea of feature modularity, right? So the point of, or the issue of what to do with that coordination code, that's nicely captured in the so-called optional feature problem, which can be read here. And there are quite a couple of solutions with different strengths and weaknesses of the questions what to do with that coordination code. You could put it here, you could put it there, you could put it in a module, and there are other solutions, right? And the point is that's not a problem of an undesired or unknown feature interactions. That applies to known, planned, desired feature interactions too. It's really, you have a kind of exponential blow-up problem here. And if you're interested in that, then look at this paper. What I would like to do here is to talk about also, of course, undesired interactions, which are often unknown. Because if you would know these interactions, then you could resolve them and it would end up with the optional feature problem. Okay, here we have, again, a canonical example of an undesired feature interaction, which is actually described in Robert Hall's paper, who described feature interactions in email systems at AT&T as a kind of experience report, what happened at AT&T with email systems. So here we have the example of encryption and forwarding, and it may happen that if you send an encrypted email to a host who is the forwarding host, this host may send that email to a third party without encrypting that email, because that host does not have the public key of the third party host. And you may say, well, that's a kind of stupid, right? Why is it doing that? The point is these features have been implemented independently, and the developers just did not think of that situation. And then that happened. And that's what Robert Hall is describing here. And that, of course, does not adhere to the specification, right? Because then a confidential email is sent in plain text. And you may say, well, that happened at AT&T in the 2000s, and well, once we know that that doesn't happen anymore. And the interesting point is that we have a nice bug report here that's from Enigmail from 2014. So Enigmail is a PGP plugin of Mozilla Thunderbird, which is widely used. And you don't need to read all of that. And the important point is here, an email with only BCC recipients is sent in plain text. So here the BCC feature is interacting with the encryption feature in a very similar way. And of course, once you know that, that can be fixed, right? You can do something about that. But the people weren't aware, because if you have a set of features, you don't know which features are interacting in an undesired way, right? And there may be many features. So these things happen. So the point is, how do we find these undesired interactions in the face of that exponential blow-up? Before I talk about that, I will tell you a little side story. There are often discussions on feature interactions, and we had nice discussions with Don and Sriram and Pamela at a couple of Dutch seminars, very heated discussions. And the point is there's actually a whole zoo of different kinds of feature interactions, regardless of they are undesired or desired, right? So we can have something like that, right? Like have a feature encryption here, and that satisfies a specification, which essentially in temporal logic, for example, says, well, that needs to be encrypted, right, in any case. So, and that feature forwarding also satisfies the specification, but once you compose it, it does not satisfy the specification anymore, and people use critical pair analysis and model checking and theory improving to find those situations. But there are also other kinds of interactions, for example, at the level of non-functional properties, and not necessarily with regard to specifications. So just think of that example. We have a database system, and we measure, that's the pi, the compression feature, right? With regard to a certain standard workload profile, like the TCP/H benchmark, which is a standard benchmark in databases, 50 seconds, and we do that also for encryption, right? We want to encrypt data, but once we compose the two, somehow the observed performance is not just the sum of the two, right? And you certainly say, well, that's clear because they somehow interact, right? Well, that's a feature interaction because they work on the same resource. That's also feature interaction. It's not necessarily, come in, it's not necessarily about a specification, right? And then we have also that corpus of work which is more at the code level, right? So the point is that feature interactions may manifest at the level of source code, right? So if we look at the implementation of BusyBox, which is that real-world system, so these Unix tools for embedded systems, then you encounter those pieces of code, right? Here we have code that coordinates two features, the feature human readable and the feature DF fancy, whatever they do. And that code is really only there if these two features are selected or activated, right? And that is responsible for coordinating the two. So in this sense, that's a manifestation of the interaction of the two features, which of course arises only at program execution. And that's of course related to cross-cutting, right? Here we have tangling. And you can have the same at the level of control flow. Here we have two features, or simplified, of course, simplified implementations, two functions, one of the feature inbox, one of the feature forward, and the two functions call each other. The point is that there's no code tangling, but of course, that control flow from feature forward to inbox is only there if the two features are there, right? So that's an interaction between the two features, and the kind that control flow dependency is a manifestation of the interaction of the forwarding feature and the inbox feature. And you can have the same also at the level of the data flow, right? In this sense, this control flow and this data flow are conditional manifestations of feature interactions. The interesting point is that when people argue about feature interactions, they sometimes confuse the different members of the zoo, right? The different animals of the zoo. It's just important to know. So that's the takeaway message, right? So there's a whole zoo and of different kinds of feature interactions, and you should be aware of that when arguing with your colleague. So, of course, we have seen there are desired interactions, undesired interactions, and different kinds of interactions in the zoo. So we want to efficiently detect and reason about feature interactions. And again, that does not apply only to undesired interaction, right? It's the same problem for desired interactions. And how do we do that? And I try to keep that part short. Here are the canonical examples from the product line community. Well, with only a few features, right, you can come up with very many feature combinations you need to look at, you need to reason about, right? And that quickly explodes. The point is, with modularity, did we really cause spirits that we can't control anymore? And what would you do, right? So as a thought experiment, so in order to really understand the feature interactions in a system, you would need to create every possible feature combination, right? You could do that, and then you could do standard analysis, model checking, testing, or just manual code review, right? And then you would know what's going on, hopefully. And well, here's also a standard slide, right? That thought experiment. If you would do that for SQLite, you would, for example, want to know performance interactions in SQLite, which is very important for database guys. Well, if you would do it in a brute force way, you would need to start at the Big Bang, right? And you would not be done until now, only after 10 to the power of 21 years, which is certainly too late, right? So what do people do in practice? Well, people do sampling, right? They somehow try to guess which combinations of features give rise to interesting interactions. And then they try to make educated guesses about the presence and absence of interactions between other combinations which we did not look at. And of course, you can do that with model checking, testing, or just looking intensively at the code, right? So, but I would like, so that's often called sampling, right? And that's heavily done in practice. I would like to just mention also a third alternative that has been developed by a quite small community in the last 5 years. That's called variability-aware analysis. That's essentially a white box approach, right? For that approach, you need all the modules, and you need the code, And then what you can do is you can do code analysis and the analysis of the variability, right? The possible combinations, you know that, in order to come up with a similar statement, right? So you look at all the modules you have and all the possible combinations, you know which module may communicate with which other module or maybe selected together with other module, and then you try to derive a statement about that. Today, I'm not talking about these three different ways to efficiently reason about feature interactions. So there's a nice survey in ACM Computing Service about that. That's written in terms of product lines, but it applies to any kind of module system or configurable system, right? And I had also a keynote at CBSoft 2014, so if you have attended that, so somebody from Brazil here, no. I did talk, so I do not want to repeat that anymore. But I will show you examples of the two in two later case studies, but I do not dig into the details. But there's, of course, lots of details to talk about when you talk about sampling and variability-aware analysis. What I would like to do today is to answer three other questions. So it's actually very easy to always talk about the worst case, right? There's that exponential blow-up, there's that feature combinatorics problem. The question is actually which kinds of interactions occur in practice. Is it really a practical problem? Because somehow we can deal with systems like Linux, which has 10,000 features plus. So what's going on in practice, right? What are the properties of the feature interactions occur in practice? What can we learn from them for building tools, right? Building development methodologies. And that's what I would like to address in the remaining talk in terms of two case studies, right? We have more case studies, actually case studies on every member of that zoo, but I talk here about two case studies. So first case studies, we wanted to study interactions in the control flow, so which are manifestations of feature interactions. How to do that, right? You need to do control flow analysis. Let's start with a very simple example. It is implemented with a C preprocessor. So we have two conditional statements here. And now you may say, where are the aspects, where are the modules? The point is, it doesn't matter, right? You could pull out that code into an aspect, and you would get the same result with regard to the control flow analysis, right? So then you can also leave it in for simplicity and just use the preprocessor. But the remaining picture here for that case study would be exactly the same if using feature modules or aspects. So what we want to do here is control flow analysis, but of course we do not want to do brute force analysis. That means we do not want to create all the combinations of possible code here in order to find out the possible control flows or possibly conditional control flows between the two features, A and B. And observe, we have nesting here, right? So that code belongs to feature A and B, right? So what we do is we create a program representation that maintains this variability, but that is amendable to control flow analysis. So we want a control flow graph that has variability, right? So it's sometimes also called variational control flow graph. So control flow graph has edges for each statement and has nodes for each statement, and the edges are the successor relations, right? The successor of int c equals a is this if statement. And here it's getting interesting that the successor of the if statement is c plus equals a, but only if feature A is selected. If not, it's returned c. And here it's getting even more interesting. The successor of c plus equals a is c plus equals b, but only if A and B are selected. So now I explained the stuff in terms of variability. But if you think about interactions, these so-called presence conditions, and Christoph coined that term, tell you about interactions, right? So here we see that the features A and B interact at the level of the control flow. And once we do that analysis, we know about that interaction. By the way, we use the tool TypeChef for that, which has been developed by Christian Kestner, and we extended it for variability-aware control flow analysis. The important point is that it really works for real-world C programs with all kinds of if-defs and preprocessor directives. So you can talk a lot about efficiency here. You can compare variability-aware analysis, how to implement kind of liveness analysis, static analysis on top of that. So I do not talk about that here. I just talk about the results. So we looked for interactions at the level of control flow for a couple of real-world systems: BusyBox, Linux, OpenSSL, SQLite. Here just one example for Linux, right? It's basically a histogram, so that's the number of interactions, and that's the interaction strength, which is basically the number of features participating in an interaction. So 2 means it's a pairwise interaction. And here see the number of interactions we found between 2 features, and that's very many, right, for Linux. And that's, in a sense, not surprising, because features should interact, right? They should do something good together. But that's really very many, and it's not only interaction between pairs of features, it's up to 14 features that give rise to unique control flows. The point is that these control flows are not necessarily bad, right? So that's desired. So in the next step, we were interested in what are potentially bad or problematic control flows. So what we did on top of TypeShift, we implemented a couple of standard static program analysis, right, based on that nice book. So we re-implemented or implemented a monotone framework in order to identify double freeing, uninitialized variables, so that may signal potentially problematic situations. And then we looked for these problematic situations, essentially for the same systems. Here we have, again, a snapshot of Linux, and still very many, right? So we have thousands of potentially problematic interactions between, in some part, many features, right? Up to 12. And now the experts in the room say, well, that's static analysis. You may have lots of false positives, right? So what does it tell us here? Well, what we did in order to counter that argument is we looked at bug databases, right? So for a couple of systems, Apache web server, CVS, Bash, Linux, and others, and there we looked whether these bugs that have been confirmed by the developers are associated to interactions between features, right? And of course, it's less, but still there are bugs, even in systems like Linux, right, where you have, for example, a couple of interactions that give rise to a bug, and that interaction needs 5 features to activate, right? These feature interactions are out there. And that somehow counters the standard argument of the feature interaction community, who said, well, interactions mainly occur between pairs of features, and we do not really know about interactions that are higher order in that sense. But these things happen. Maybe they don't know about them because they did not look at this. Right? So feature interactions occur in practice, and not only between pairs of features. Right? Okay, let me talk about a second case study. And the second case study is interesting because we didn't start with interactions. We didn't think about interactions. We wanted to do performance prediction for configurable systems, right? So for configurable systems, it's inherently hard to know which configuration is the fastest for a certain setting, right? So which options do I need to activate in my database system so that it is fast for a certain workload? So typically you have a partial feature selection, a workload, and an objective function, which is for databases maximize performance. And then you want to create a performance model to answer questions like that. What is the fastest configuration in a given setting? And that's what we wanted to do. It was not about feature interactions, right? And well, we cannot measure all configurations. It's an exponential number. So we said, let's do a very simple approach, right? So let's start with determining the influences of individual features, right? And then to make sense of the whole thing. So what we do here, for example, for a database system with 3 features, compression, encryption, transactions, we can, with regard to a certain workload profile, measure, right, the base database and the database with compression. And then we simply say, well, the delta, that's the influence of that feature. We simply state that. We assign that value to the feature. So we use here, that's measurement, that's the delta we calculated. And then we do that for the other 2 features. two optional features. And okay, that's a linear number of measurements. And now we want to do prediction. Prediction is phi. And here we want to predict the performance of this configuration. And notice that we did not measure that configuration before. We want to predict the performance. And we do that based on the existing results. And here we are very silly, right? We just add them. And we predict, well, the performance should be 160 seconds. And the point is, what? Is that really that simple? And of course, it's not. Because if you predict performance for a certain configuration and then test that, right? So do a try and error approach. We predict the performance based on that simple approach and then we test that. You may find that it is not correct, right? You may find for that configuration the prediction is 150 seconds and now we say, well, let's test that, let's measure it, and we get 140 seconds. So what's going on? Here's certainly something going on that we did not expect. And the point is, well, there's syn interaction, right? So because encrypting compressed data is different from encrypting non-compressed data. And that's, in this case, a known interaction, right? The point is that this delta-based approach and the try and error approach are means to detect feature interactions. And these feature interactions are important to improve the predictive power. So we did that approach. And there are, of course, more details, and you have to look in the paper how that really works. Here's just an example for SQLite. Right? So we did that for SQLite, and the nodes are the features of SQLite, and the edges are the pairwise interactions that we found with that approach. Right? And the first observation is most features do not interact at all. No, that's with regard to performance. That's nice. And some interact. And if we change the layout, then we see, wow, there seem to be some interesting features here, like OMT complete, right? So we better look at them when looking for higher order interactions, because pairwise interactions are just part of the story, right? And in that paper, we explain how we use that model, it's a kind of network analysis, in order also to identify higher order interactions. What I would like to do here is just to briefly summarize the results. The first important thing is with that approach we can create so-called performance influence models, right? We can, based on the measurements, come up with a formula that characterizes the performance of the configuration space as a whole. And here the point is parts of that formula correspond to the influences of individual features, but also of a feature interaction. And basically, that's a machine learning approach. And we use much more machine learning in the background. Here it's just a simple version of that. And the interesting thing is that feature interactions then correspond to higher order effects in machine learning, right? So somehow relate the two fields. And here we have an effect of a feature interaction. And the point is we need feature interactions. We need to identify feature interactions in order to come up with good predictions. So in this sense, feature interactions are a means to make good predictions and to do performance optimization in the end. And we did that for a couple of systems, and I do not want to go over all the results. Just one example. If you want to have accurate predictions for SQLite, you need to do a full population analysis. I told you that takes time. But if you use our approach, you can invest 2 days of measurement with an accuracy of 93%, which is not perfect, but reasonable. All right? And feature interactions are at the heart of that approach. So, okay, that's the application, but what is about the actual feature interactions we identified, right? So we did that for a couple of systems, even more systems than I've shown you on the slides before. And it's again a histogram here. For example, we see that for a Berkeley DB, right, and the interaction strength. And of course, we have interactions between more than 2 features that are performance relevant. And these things exist, right, in practice. So we have also a nice tool which you can use for that. It's called SPL Conqueror. It does the sampling for you, the machine learning, and it has nice visualizations, and works also for numeric parameters, not only for binary features, so it somehow then diverged from the feature-oriented idea. But anyway, you can have a look at this. It's very fancy. The point is, the takeaway message, feature interactions occur in practice, and not only, and also at the level of non-functional properties. Okay, that's nice. But where do we go from here, right? So we did 2 case studies, and actually we did more case studies also at the level of source code and the level of functional feature interactions. But where do we go from here? And to me personally, and that's a kind of also personal agenda, the techniques we have and the insights we can gather with these techniques give rise to the new feature interaction challenge. So what we have currently is we have information on control flow interactions, data flow interactions, manifestations of interactions at the level of source code, right? And we have, of course, the whole arsenal of techniques for identifying functional feature interactions based on sampling, but also based on variability-aware analysis using model checking, testing, and so on. And we have developed machine learning approaches, not only us, to learn about non-functional feature interactions, not only for performance, but also for energy or memory consumption. And that works. So that is, we have different views on what's going on with regard to interactions in a system, right? In a modular system or a configurable system in general. And the point I want to make here is that it takes a lot of innovations to arrive at that picture. So different communities needed to implement different techniques for variability-aware analysis, machine learning, search-based software engineering, to start to answer a couple of interesting questions. And we're not able to do that 5 years ago. We're really currently at that point. And we can start talking about properties and distributions of interactions, different kinds of interactions. But more interesting is correlations. Are there somehow correlations between different kinds of interactions? So is it the case when I observe performance interactions between 3 features that there's lots of data flow between them, lots of control flow? And prediction, of course. Is it the case that I can predict the presence or the likelihood for a certain kind of interaction based on the presence of other interactions? So is it the case then when I observe heavy control flow that I should look for functional feature interactions? And you can speculate a lot, right? But it's not clear. But there's a promise, right? Here's a lot of promise in. And the new feature interaction challenge is to answer these questions for a couple of real-world systems, of course, as many systems as possible, using these novel techniques. And they need to be improved too, right? And that's the final takeaway message, right? Different kinds of feature interactions are potentially related. Take advantage of that, because it's easier to learn about certain kinds than about other kinds of feature interactions. I want to do prediction. And, well, that's the summary. I do not repeat it, I just give you that visual picture. And that's it. Thank you very much. By the way, here are all the contributors of that talk are also co-authors. So the picture stays, of course, the same, but you need the information. So we mainly look at software system because the information is there. But we have a collaboration with Bosch, which is also about cyber-physical systems. And some of these analysis approaches, which are the basis, right, for determining feature interactions, do not work then anymore. So either you do not have access to the code, or some interactions appear at the level of hardware or in the physical world. So for example, we look for interactions at the level of emission, right, in engine control systems. So that's right, but well, the point is that you need to improve the individual analysis techniques and models. So that's not really a problem, for the validity of that challenge, but it contributes to the challenge. So arriving at this point only for software was very challenging. You know, to parse and analyze a system like Linux with all variability is very challenging. And we have much more challenges. And we are working on that, and we hope that the whole community is contributing, right? And that's a key point here, right? It's not that we want to do that. We can't do that, right? You need different analysis tools, and different case studies to contribute to that bigger picture. So that's a frequently asked question. So the point is we are from the modularity product line field, right? There's a whole community on performance engineering, people who really address those problems. So what our unique contribution is to put feature interactions in the center. And then, of course, we need to apply all the innovations from the performance engineering community to our work, which we did not do so far. For example, currently we concentrate on application domains where there are standardized benchmarks and workload profiles. It's not the case for any domain. But then you can use standard techniques from performance engineering, right, to model the workloads. So we experimented, for example, with integrating the workload and the workload variability, which may be variable, of course, into that approach. But that's a kind of additional topic that does not really change the big picture. But of course, like in model checking for functional feature interaction, we need, of course, need to use these state-of-the-art techniques from the respective field. And we do our best, but it's very hard, right, to keep track with whole communities. But that's a good point, right? You need to do that. Chaos. Yeah, well, the important point for me and also for the talk was just to raise awareness that there are multiple kinds of feature interactions. So we wanted to avoid to come up with another classification of feature interactions. So it was actually sports in the feature interaction community to come up with classifications of feature interactions. We want to avoid that. So I'm not sure because you can, in detail, you can argue a lot about it's not really a classification, but you can argue about what is functional, what is non-functional. Let's not go into that discussion, right? So it's actually, there are blurring boundaries between them. It's important to know that there are different manifestations of interactions, and we should use all of them to complete the picture. Whether a better structure for the zoo can help with that, I don't know, I believe, but I do not feel that I should, organize a zoo. That may be the case, I think, for certain kind of interactions, especially the ones that are closer to the source code. You can have that. But in the end, you have to see, for example, for a Java product line or Java program, that also the JVM is a kind of transformation. So it takes the bytecode and then it creates the runtime representation of the program, the running program. And there it's very hard to reason about properties because in the end it's an undecidable problem and you will have certainly less nice algebraic properties than, for example, going from source code to bytecode. But it's certainly worthwhile to look for that. What you're talking about essentially is that you want to kind of understand how these different pictures contribute to the overall picture, big picture, whether there's a kind of algebraic rules, right, where you can go from the different angles of that picture. And that's certainly a worthwhile approach, but that's all I can say for now, but because you really need to look at the details, right? For some, yes. For some, I mean, you can always come up with an algebraic structure modeling them. The question is how rich the algebraic structure will be, right? So what guarantees you can have. I mean, you cannot even have, in the end...
It doesn't necessarily have to be rich, but can it be useful to explain?
Yeah, yes, that's right. That's what I mean with richness, right? So it may be less rich than you need for interesting observations. But we don't know, right? Yeah, well, microservices, well, it is a way to implement a system in terms of modular units, and the micro means the modules are very small, right? So yeah, that's a relation. There's also, I mean, that observation from Ted Bigger stuff from the 90s, right, who says, so, well, if you do the modules so small, then you do not have so much benefit from reuse. And if you do them big, you have lots of benefit, but you can't combine them in different ways. So that's all I can say about that. But you talked also about interfaces. Is there another question? Yeah, well, that's right. So that's especially the question where the programming language community, for example, is interested in. Can I come up with programming language mechanisms that help you to build feature implementations or modules that interact less? So that somehow narrow down what a programmer can do to avoid certain kinds of interactions. But that's only for some kinds of interactions. So, well, two features can always open a file, right, and do something with the file. So you cannot catch that with a reasonable type system or any other kind of approach. But you can try to avoid certain kinds of interactions by prohibiting global variables and those things, having a strong type system. That's certainly clear, and that applies also to microservices, having well-defined interfaces, and so on. And you can do those things to avoid certain kinds of interactions, but only certain kinds. And of course, if you have a certain implementation mechanism that helps you to avoid certain kinds of interactions, then you can ignore those, right, during the analysis, which helps, right? Because then, you know, these things can't happen, and that scales the whole thing. It's also about scalability, and it's good for program comprehension. But other kinds of interactions will occur.